Hi guys, welcome back to Data Every Day. Today we're looking at a data set of crowdfunding loans from Kiva. So basically we have a bunch of different loans that were given through crowdfunding, and we're going to try to predict the type of loan. So if we look in here, there is one column called repayment interval, and in here we have bullet loans, weekly loans, monthly loans, and irregular loans. So we're going to try to predict which type of loan it is based on the other features. So let's hop into the notebook. We're going to be using TensorFlow today to build a neural network. And I'm importing NumPy and pandas just for working with the data. Then matplotlib.pyplot and seaborn for visualization. And then we'll use the train test split function and standard scaler from sklearn for preprocessing. For our model, like I said, we use TensorFlow, and then I'm just importing the confusion matrix and classification report from sklearn for analyzing the results of our model. So let's go ahead and import those, and I'll load in data using pandas.readcsv. I can grab the file path up here. I'm using kivaloans.csv, so I'm pasting that in, and we can take a look. And I believe this dataset has quite a few rows. At least for Kaggle, we have 671,000 examples, which is a good number. And let's get a little info on each column using data.info. You can see we definitely have some missing values here. These are all different numbers. We also have a fair number of object columns, 14 different object columns that we're going to have to encode in some way. So let's get into it. I'm going to create a bunch of helper functions today that will help us in our pre-processing and analyzing of the model. So the first one I'm going to use is pre-process inputs. And that's going to take in a data frame, and it's going to make a copy of the data frame, and right now it's just going to return that data frame. So down here in pre-processing, we're going to run this function, preprocess inputs, and we're going to pass in our data. And I'm going to call the preprocessed version of the data x, and we can take a look at x down here. So currently x is just a copy of data, right? Same data frame. But now as we add steps into this function and we run this, we'll get changes made to x. So whenever we're dealing with a fairly big data set like this with a lot of different kinds of columns, I like to get two bits of information before we start. One is going to be the missing values in the dataset. So we can call x.isNA to get a true-false matrix of where there will be a true value wherever we have a missing value. And I can sum this over the row axis, axis 0, in order to count up all the trues in each column, and therefore get the number of missing values in each column. However, what's even more useful than seeing the counts is getting the percentage of missing values in each column, which we can get from the mean function. So this will add up all the trues and then divide by the total number to give us the percentage of missing values in each column. And you can see we actually don't have any columns here with a really high amount, the highest being the tags column that has 25% missing values. And I probably will drop this. In fact, I will drop it not only because it has missing values, but because I want to avoid doing any natural language processing today, only for the reason of time. Don't want to go into that. So this use column is also I'm going to drop. Okay, so tags and use we know we're going to drop, and then the rest of them, I believe these are low enough numbers that we can definitely just fill them in with the means of the columns. So the other bit of information I like to get is the number of unique values in each column. So for this, we can get a dictionary that's going to map a column name to the length of unique values in that column. So I'm doing x sub column dot unique and taking the length, and I'm mapping a column name to that each time for every column in x.columns. And now we basically get a dictionary that maps each column name to how many unique values are in that column. This is very useful information to have. So you can see our what we're trying to predict here, the repayment interval. We only have 4 values. Like we saw, we have bullet loans, weekly loans, monthly loans, and irregular loans. However, for the rest, we have quite a few unique values. In some of them, we have a very high number. So we have to be careful what we're looking at here. Some of these are numerical. For example, the posted time. Well, it's not exactly numerical, but it makes sense that each of these is unique because we're not going to we're not considering it as a categorical column. So let's continue. The ID column. The ID column has actually the maximum number of unique values. You see this means that every single loan has a unique ID, and therefore this column is not useful because it doesn't provide any sort of new information to the dataset, since there's no way to draw comparisons between examples. So I'm going to drop the ID column. So in our preprocessing function, we'll say drop ID column. Yeah, I don't need to specify a reason. It's fairly self-explanatory. We do that with df.drop ID. I'm dropping from axis 1. Then I'm also going to drop the natural language processing columns. Drop, I think it was use, and what was the other one? Other one is tags. Use and tags. Tags columns, avoiding NLP. So df equals df.drop, use tags, axis 1. Okay, now if we look at this, you can see we have those columns have been removed, and now we want to continue looking. First, we'd like to sort of figure out if we have any redundant columns. Sometimes we can have the same information encoded in 2 different columns. So for example, I can see it right here, country code and country are actually redundant. They're both saying exactly the same thing. This is just saying it in a more concise way. And you can see, we can confirm that down here. We can see there's 87 unique values in each one. So I'm going to drop country, and I'll keep country code. But we could keep either one, doesn't really matter. So drop country column, and I want to check for any other ones. I think there's one more in here, which is the date column. You can see that the posted time actually contains the date inside it already. And this is always just a copy of this. I double checked this already, it is exactly the same. So let's go ahead and remove the date column because it is redundant as well. So drop country and date columns. So df equals df.drop country and date from axis 1. And this is because of redundant information. Alright, there we go. Let's take a look. Now, this is our data set. So we have 15 columns now, and it's definitely workable. I guess we should take a look now at if we have any high cardinality columns. So what I mean by that is within our categorical columns. So a categorical column is a column with text labels like this, or it could also be something like this that has numerical labels, but we know that these are IDs, and each one is independent of the others. So this is also categorical. We want to make sure that the cardinality of our categorical columns isn't too high. And mainly this is, especially in this case, it's because we don't have unlimited training resources and time, and the higher cardinality of a categorical column, the slower the training will be, and you also need a more complex model to handle it. So we are using a deep neural network today, so high cardinality isn't really a problem. However, Kaggle does have a cap on how much memory you can use, so we're trying to limit high cardinality columns. And if we're looking in here, we can get this, basically we can limit this down to just looking at the categorical columns by typing x.select dtypes object.columns instead of just all columns. So this will just get the object columns. And before I do that, I just want to note the only categorical column here that is not an object is the partner ID. So I'm just going to go ahead and look at that. And we have, where is it here? This is not so bad. So a cardinality of 367 is quite low. That's manageable. But now I want to go ahead and see all the ones other than that are objects. And okay, let's see. So the time columns, these are not categorical, right? We have to be careful. The time columns are actually datetime. They're datetime data, and we can extract separate continuous features from them. So we don't want to consider these as categorical. However, activity is categorical, sector is, etc. So these are all reasonable. However, region, this is a high cardinality column. This has 12,600 examples. And the reason we don't want to use this is because the way we would encode this, I mean, there are multiple ways of encoding it, but if we're just using a standard one-hot encoding, we can do that with pandas.getDummies. Let's pass in that column, so it's called region. If we wanted to get the dummies for it, you can see it's taking quite a bit of time. But you can see now we have 12,000 new columns, one for each separate region, that we would have to add to our dataset. And so training on a dataset with 12,000 plus columns is going to be a lot slower than compared to just not using this. So for our purposes, we're not going to use it. However, you can note that we have 671,000 different examples, and there's only 12,000 different regions. So if we did have access to unlimited time and computational power, I definitely include this column because it does have some useful information in it. However, for our purposes, we're going to drop it. So over here, drop region column, high cardinality. df equals df.drop region from axis 1. Okay, and I think that's it for feature selection in terms of limiting, at least in terms of limiting out the unnecessary or useless features. So let's look at what we have left. So I guess the next thing I'd like to do is deal with these date columns, these datetime columns. So I'd like to note that we can use pandas.toDatetime and pass in one of these columns. Let's use posted time. And this will give us, oh sorry, it's not df, it's x. This will give us the same column. If we look at the original column, you can see that the data type is object, and these are actually encoded as strings. But by passing it through pandas.toDatetime, it encodes it as a datetime64 object. And this is a very nice data type because it allows us to do the following. It allows us to apply a lambda function to it that takes in a given x, which is going to be one of these, and return x.year if we want the year. And you can see that's just the year from here. X.month if we want the month, and that takes the month from here, and so on. However, if we were just doing that with strings, we'd have to either index like this. We'd have to say x goes to x from the first 4 characters of x, so that would get the year. And this is a lot more cumbersome and annoying, so by turning it into a datetime column, it allows us to get it much more easily. So what I'd like to do is create a function in our helper functions called encodeDates. And we're basically going to pass in a data frame, a column we'd like to encode, and that's it. And we'll start by creating a copy of our data frame. It's just a good practice to get into so that we're not accidentally modifying the original data frame we're passing in. We want a fresh copy. And then I'm going to take the column and first convert it to datetime using pandas.toDatetime of the column. Alright, and then I'd like to create 6 new columns for each one. So I'm going to take the year, month, day, hour, minute, and second columns. Now, you could say second probably doesn't have much useful information, but that's okay. The model will figure that out. And we're not dealing with so many columns here that it's going to cause the model to overfit harshly. but you probably definitely don't need the second. I'm just doing it for instructional purposes. So we take, we're going to create a new column now. So we're going to reference a new column that hasn't been created yet, and that's going to be given by column plus a string concatenated to it with underscore year. This will be the year column. So if we pass in posted date as posted time as the column, that'll come in posted time, posted time, posted time, and then df sub posted time year. You see, we'll add year to the end of posted time to give us a new column name, and then we'll take the old column, which will be df sub column, and apply a lambda function to it that turns x into x.year. And we're going to do the same thing for month, day, hour, minute, and second. So this will be underscore month and dot month. This will be underscore day and dot day. This will be underscore hour and dot hour. This will be underscore minute and dot minute. This will be underscore second and dot second. And then when we're done, we're going to drop the original column because we no longer need it. We've extracted all the information from it that we want. So I'm dropping the column and returning df. And now if we basically call this on all of our datetime columns in our preprocessing function, so we'll say extract date features, and df equals encode dates, and we're going to pass in df, and the column is going to be, first we'll do posted time as our column, then we'll copy that over once for dispersed time and then once for funded time. So here's dispersed time and here is funded time. Alright, let's run this, take a look. And as soon as that's done, we should see that we have our date time columns at the end here, the year, month, day, hour, minute, second for each one. And you can see we can no longer see all the columns, so I'm actually going to go into the console and type pandas.set option, max columns, none. And that will allow us to reload X and see all of the columns at once. And you can see we have all of these date time columns now, and the original date columns are gone. So if we run this, you'll see that our set of object columns has gone down. We only have a few left, and the cardinalities of these are reasonable, except for this one. However, this is a sort of interesting column. This isn't exactly categorical. I mean, it is to some degree, but look at what we have here. This is actually including the genders of every borrower for the loan. So let's take a closer look at it. Borrower genders. You can see we can have multiple entries, right, in each one. So if I want to get all the unique values in here, you can see some of these entries are extremely long and contain a whole bunch of borrowers. So what I like to do here is not one-hot encode this, because first of all we lose some information there, because the model wouldn't be able to see how something like this and something like this are similar. It wouldn't understand the values within each one, but also because it has a very high cardinality. So what I'd like to do instead is sort of engineer two new features from this column. One will be the number of male borrowers in a given loan, and the other will be the number of female borrowers in a given loan. So what we're going to do is create some new functions up here, get male counts and get female counts. And at the beginning, okay, so this is actually going to be, these are functions we're going to pass into our into apply. So we can apply to a column like we did up here. Where is it? Up here. Dot apply. So you can apply a lambda function, but you can also apply a function of your own creation, but it should take in a single value like this, where the value is going to be a given entry from the column. So this will be our x in this case, our x, our x, our x, going down. And we want to take this x, which over here, which in this case x is going to be a list, actually is a string of different borrower genders separated by commas and spaces. So what I like to do is turn this into a list. I'm going to split it. Here, let's take one as an example. Let's grab this one here. So I'm going to grab that, and this is going to be our sample x. So let's say x equals. I'll call it z for this. So z looks like this, and if we split z on comma space, it will split on comma space like that, and we'll get a list of all the different genders. We can then sum up the number of each kind like this. So we're going to take in our x and split it, and then say for each gender in x.split on comma space. So for each one of these now, we're going to increment the count. So we'll count will be initialized to 0, and then count if gender equals male, count plus equals 0, plus equals 1, sorry. So we're adding 1 to count if we have a male for each one of these. And by the end, we'll have the total number of males in a given loan. So I'm just going to copy that over. The same for female, except here we'll have if gender equals female. And so this is what we're going to do. Let's see if it works. We're going to run that, and then over here, say engineer gender count features. And we're going to take the male count. We're going to create a male count column that will take the borrower genders column and apply our get male count function. And then I'm going to do a very similar thing for the female count. This will be female count, and we will apply the get female count function. And let's take a look at what happens. Get male count is not defined. Oh, this should be count. Count. Yeah, okay. Okay. So just take a second. Oh, what is this? Float. Oh, okay. So there are some missing values in here. We can double check that over here. Yeah, we have some missing values. And obviously we can't split a missing value. So what we can do instead is turn it into a string first. String of x dot split. And that will just, even the missing values when turned into a string will just become NaN in all lowercase. So this should fix the problem, because then if you split it and there's no comma space, it's not going to affect it at all. So let's try that one more time. Take a look when it finishes. And we have this column here, but we now have our, okay, it didn't work. So the fact that it's done means maybe we didn't return something. Okay, yeah, we didn't return the counts. Sorry. Okay, on both of these, let's return count. And now let's try it. This should work. And then, okay. Alright, let's see. Yeah, here it is. Okay, here are our counts. And we can compare. You can see we have one female here, two females here, and a missing value here. Over here we have 1, 2, and 0 for the missing value. So we can assume that the same thing's going on with male. And so now we basically have two useful features that came from this original sort of unuseful feature. So it also encoded the missing values all by itself, because now it just has zeros if there's a missing value in that column. So now let's drop this. We don't need it any longer. So over here, df equals df.drop, borrower genders, axis 1. Alright, and now I guess it's time to one-hot encode. Because if we look at the object columns now, you see we only have a few left and no more high cardinality columns. These are all perfect candidates for one-hot columns, except for this one. We don't want to one-hot encode that because that's what we're trying to predict, and we want to treat that as a label column instead. But these guys are good to go. So I'm going to copy that, and up here I'm going to sort of save it in here I'm going to say one hot encode nominal features, and then I'll create a nominal features. I'll make it a list of features for now. I'm just going to bring them back, and then indent, and delete these things at the end. And then, yeah, commas. Okay. So, for each one of these, we're going to apply our one hot encoding. So let's create a function called one hot encode, and it's going to take in a data frame, and I'm going to pass in a list of columns with prefixes. So before I showed you pandas.getDummies. Let's take one of these one hot columns, for example, country code. Let's use that. So x sub country code, this will give us a list of new dummy columns. For each country code, we'll have a new column. Why is this taking so long? This is strange. This is working, right? Hold on, let me restart the notebook. I don't think it should be taking this long. Okay. Sorry about that. Let's just start this up again as soon as the draft session starts. Alright, run all. Okay, here it is. So I guess it froze on us before. These are the dummy columns for the country code. So each country code gets its own unique column. And then we have one hot vectors for a given example. We have to re-enable the max columns setting real quick since we restarted the notebook. And rerun. And you can see there will be a given one in a given the ones will correspond to the original value of an example. So over here in data, we have Pakistan, and then down here we have 1, 1 in that column. So the reason I bring this up is we can use a prefix to set, let's say, country code as our prefix, and that will put country code at the beginning of each column name. And this is useful for knowing where the columns are originally coming from. So let's implement this in our function up here. So I'm going to start by creating a copy of our data frame, and then I'm going to create the dummies like I just did. Sorry, I'm not going to pass in column. I'm going to pass in columns with prefixes. So I'm going to pass in each prefix along with a given column as a tuple. So this will be a list of tuples where each tuple represents a column and its corresponding prefix. So I'm going to iterate through for each column and prefix in columns with prefixes. We'll create some dummies using pandas.getDummies for a given column using a given prefix. Once we've created the dummies, I want to add it to our data set. I want to concatenate it. So pandas.concat, the original data frame and the new dummies columns side by side. So axis 1. Then we will drop the original column from which we created the dummies. And once that's done, let's return df. And this is a one hot encode function that we can now use to encode all of these nominal features. However, I want to add in all the prefixes, so I got to pass those in as well. So for activity, we'll give it a prefix of act. For sector, we'll give it a prefix of sec. For country code, we'll give it a prefix of ctc. For currency, we'll give it a prefix of cur. And I think there's one more categorical here. That would be the where is it? There's an ID here. Oh, partner ID. So this is a numerical categorical variable. The categories are represented as numbers, but it is an ID. This is categorical. So over here we have partner ID, and I'll give that PID as the prefix. So now let's just do that with our one hot encode function. I'm going to pass in df, and then our columns with prefixes list is going to be nominal features. Let's see how that goes. So we're looking at X now, and I'm pretty sure after this we're pretty much done. Oh, tuple object is not callable. Oh, I forgot to put commas. Okay. That should work. Yeah, like I think that should be most of the encoding, because I think after this all the data will be numeric. So let's see that. This is taking longer and longer just because we have so many rows. Okay, so it looks like, yeah, it looks like all of our data is numerical except for our target column, which is fine. All we can see, we have all these new one-hot columns at the end. These are all the dummies columns that we created, and the original columns that are not categorical are still here at the beginning. We now have 722 columns. So we can check how many object columns we have left by taking x.select dtypes object, and we can type .columns to see the names of them. And we only have one. That's our output column, our label column. So let's go actually encode that. But first, let's actually split the data. So we're at a point now where it would be nice to split this away from the rest of the data. So split df into x and y. Y is going to be what we're trying to predict, so just the repayment interval column, df sub repayment interval. And x is going to be everything except it. So we're going to drop it from the remaining data, and we're dropping from axis 1 and storing that in x. So y is our target column, and x is going to be all of our features, which is everything else except the target that we're going to use to try to make predictions. And then let's go ahead and encode the labels. So we're going to create a label mapping, which will be a dictionary mapping that maps a label name to a unique integer. And this is because we're using TensorFlow. TensorFlow doesn't like it if you keep the string names on like this, so we have to map it to integers. So let's see all the values in here. We'll take the repayment interval column and call .unique on it. We have 4 different values, and I'd like to sort them into a nice format, so I'm going to use bullet as our first label, then I'll do weekly, then we'll do monthly, and then we'll do irregular last. So here is our mapping. We're going to map bullet to 0, weekly to 1, monthly to 2, and irregular to 3. So each one of these will become the integer that's associated with. And it's very easy to do this. We can literally just call y equals y dot replace label mapping. And that will, the replace function allows you to pass in a dictionary that will automatically perform the mapping like this. So let's run that and take a look. And so I guess I'll pause it and resume when it finishes. All right. I realize I returned df. I actually have to return x and y instead, and then get x and y in this. So now we're returning 2 values, and x should no longer have this, and y should just be this column. So I'll try that here. All right, here we go. So x should now no longer have that column, and our y should just be the labels. And you can see it's in integer form. So we know this means a bullet loan, 3 means a regular loan, based on this mapping up here. And so this is all numeric. However, we do have some missing values still. But we know that we can't see them all, but if we look at how many are over 0, and then we can use that as an indexer, x.loc, all rows, and just those columns that have more than 0 missing values. You can see these are all the ones with missing values, but they're all numeric. So that means we can just fill in the missing values with the column means. So let's look at this. This will be the names of the columns that have missing values. So what I'm going to do is up here, just say, right here, fill in remaining missing values with column means. And this is going to be our missing value columns. is going to be the columns where the missing value, well, we could do sum instead, it's still the same effect, where there's more than 0 missing values in X. Then all we have to do is for each column in missing value columns, we can fill in the missing values of that column with the column mean. So X sub column equals X sub column dot fill NA. Fill NA will fill the missing values with whatever value we give it, and here we're giving it X sub column dot mean. So now if we return this and we get X, we should no longer have any missing values. So I'm going to check this again by doing x.isNA. This time, instead of summing over one axis, I'm going to sum over both axes to get the total number of missing values in the dataset. And that is 0. So we have no more missing values in our data. And that means we're about ready to feed it into our model. We just need to scale the data now. So I'm going to make a train test split using the train test split function from sklearn. This function will shuffle the data for us and then split it with a given train size. So we're splitting x and y with a train size of 70%. We'll keep shuffle equals true on, and we'll include a random state to ensure that the shuffle and therefore the split is always made in the same way. This can be any number. And that will return 4 new values, 4 new sets of the data: xtrain, xtest, ytrain, and ytest. And then we can return this instead. So I'm going to go ahead and return these 4 sets. Now, before I actually run this, I want to scale x with a standard scaler. So currently, if we look at x now, the mean of x, so this is the mean of each column. The means are all over the place. So we have different means in every one, and we have different variances in every one. Now I'd like to sort of standardize the columns so that they all take on the same range of values and have the same means and same variance. And that can be accomplished using a standard scaler, which will give every column a mean of 0 and a variance of 1. So I'm going to create a scalar object from sklearn, standard scaler from sklearn, and fit the scalar to the train set only, because we want to sort of assume that we only have access to the train set at the time of pre-processing. And then I'm going to use scalar.transform to transform the train set and also the test set. So I'm using scalar.transform on both the train and test set based on the fit only to the train set. And these return NumPy arrays, so I'm going to go and turn them back into data frames as well. I'd also, because we're recreating the data frame, I'm going to keep the column names. I'm going to specify the column names to be x.columns. Alright, and now we'll return this. This time we're not getting 2 values, we're getting all 4 of these. So let's get those, and then I want to take a look at xtrain once it finishes. Alright, it finished, and you can see that these columns have been scaled. We can get the means for each one, this time on xtrain. You can see the means are all extremely close to 0 now, and on the variances are all extremely close to 1. We do have one with 0. I'm not going to get into exactly why that is. It's sort of annoying. Essentially, when we did the one-hot encoding, we ended up with some columns where only one, for example, if there is only one entry in the whole column, if it ends up in the test set, and then essentially when we fit the scalar, there's only one value in the train set, which is 0, and therefore the variance is going to be 0. Don't worry about it; it's really not a big deal. But technically, you could drop this if you want to be, if you really want to go there. But we're going to proceed. So let's take a look at ytrain as well. Ytrain should just be the same thing, but 70% of the data. So xtest and xtrain contain xtest and ytest contain the other 30% of the data. Alright, and now we're ready to start training. So I'm going to create a sort of simple neural network using Keras. So I'm going to create a 2 hidden layer neural network. Inputs will be a tf.keras.input layer, where the shape will be 100. Sorry. The shape's going to be the length of a given input vector, feature vector. So that's, for example, that's a single row essentially. How many values are in a single row? We're feeding it in one example at a time or one row at a time. So we have a 721 values at a given time. And we can get that with xtrain.shape sub1, which will be this value here. And we're going to create 2 hidden layers, which will be dense layers with 128 activations each and ReLU activation function. And I'll pass in inputs to this one, and then we'll duplicate it and pass in x to that one. And we'll give it an output layer, which is also a dense layer, but this time we want to give it the number of classes that we have, which is 4. We have 4 different classes here. And I'd also just like to have a list here. Maybe we'll call it labels. Will just be a list of all the classes in the order that they go. This actually should be, what is it? Bullet. Okay, we have weekly, monthly, and irregular. Alright. Alright, so we have our model. This actually needs a softmax activation function. So that the softmax will make sure that each one of these 4 values is a probability estimate for each of our classes. So 4 different probability estimates, 1 for each class for a given example. And we'll pass in the output of x there, and we'll create our model. We'll call it model with tf.keras.model. We specify the inputs. That will just be our inputs layer, and our outputs will be our outputs layer. Then we'll compile the model. So we're going to use an atom optimizer. For loss, we'll use sparse categorical cross entropy, which is what you should use in a multi-class classification setting where you have integer labels like this. Cross entropy. And then for metrics, we'll just use accuracy. Alright, and then I'll fit the model, model.fit. I'm going to train it on xtrain ytrain. Give it a validation split of 20%. Specify a batch size of 32. We'll train it for 100 epochs, but we will employ a callback function called tf.keras.callbacks.earlystopping. And this function will take a look at a given value. Let's give it the val loss, validation loss. And when it notices the validation loss has not improved for a given number of epochs, let's say 3, it will stop the training and restore the best weights. It will restore the weights from the best epoch. And so here we go. So let's train it and see how that goes. Alright, so as it trains, I'm going to start on another helper function called evaluateModel. And for this, we're going to pass in the model and the test set. And what I want this function to do is sort of give us a sort of an idea of how well the model's doing. So we're going to get the results from evaluating the model using the model.evaluate function, passing in the x-test and y-test. And I want to set verbose equal to 0 so we don't see the TensorFlow loading thing. Then I'll print out the loss, test loss, display it to 5 decimal places, and format that with results sub 0. So results, which is a model.evaluate, this will return 2 values, the loss and the accuracy. Loss will be given by sub 0, and the accuracy will be given by sub 1. So here's test accuracy. I'll just indent this up. And then let's display this to 2 decimal places with a percent sign. And we'll make this 4 so they line up. And then for the percent sign, since it's a percent, I want to multiply this by 100. Okay, and there is the basic metrics. However, I want a better understanding, so I'm going to use a confusion matrix. So to calculate a confusion matrix, we need the predicted values for the test set. So I'm going to call that ypred. That will be model.predict xtest. So predictions made on the test set. Let's check on our model performance, our model training. All right, it's still going. And so model.predict is going to return 4 different probability values for each example. So that's because we specified 4 values. They will be probabilities that sum to 1. So the one with the highest probability will be our classification. So we could get that by taking the max of it, numpy.max over axis 1, which will get the highest probability value. But if we want the actual classification, we can do numpy.argmax, which will give us the position in the list of the highest value. So therefore, the classification label, which will be 0, 1, 2, or 3. And then we can create our confusion matrix. We can call it CM using the confusion matrix function from sklearn. We're going to pass in ytest and ypred. And then also get a classification report, which just gives us some more metrics about the confusion matrix. And that is also from sklearn, and that also takes ytest and ypred. However, we do want some target names on here. And the target names is going to be our labels here. So I'll just paste that in here. Then we're going to plot the confusion matrix using matplotlib.pyplot. So I'll create a new figure with a figure size of 10 by 10. And then I'll create a heat map seaborn, passing in the confusion matrix, turning on annotations, formatting it so that we show integer values instead of scientific notation. And then we're going to give it a color map. I'll choose blues, and then turn off the color bar. Then we're going to set the X label to predicted, and the Y label to actual. And over here, we'll give it some tick marks to show the actual target names. So X ticks. First, we'll specify the spacing. So we want a numpy A range with 4 values that will give us 0, 1, 2, 3, and 0, 1, 2, and 3. And we're going to shift it over by 0.5 so that the spacings line up into the middle of each box. Then I'll pass in the actual names of the labels right here. And I'll do exactly the same thing for the Y ticks. Alright, then we'll give it a title, confusion matrix, and we'll show the plot. And then the last thing I want to do is print out the classification report. Classification report. And I'll just include a line of hyphens at the end so it looks nice. And we'll pass in the CLR here. Alright, and that's our function. So let's hope our model has finished. Yes, it has, and you can see it called the early stopping callback because our validation loss refused to improve after 3 epochs. So it stopped and restored the weights from the best epoch. Alright, so let's take a look. Results. We can now just call evaluate model on passing in our model and the test set. Now, we probably don't need this anymore since I already specified them. I hard-coded them in there. And let's take a look. So it's just going to take a moment while it makes the predictions on the test set. And then it should print out our loss and test accuracy. You can see here, the loss is not so important to look at, but you can see our model is doing quite well, a 95% accuracy on the test set. And here's our confusion matrix. So accuracy is a little difficult. So it's a little it's not so informative. So our models, there's no doubt it's doing well, but look at what it's doing for the weekly predictions. So on the bottom here we have our predictions. So each column represents our predictions across each class. And then on the y-axis we have the actuals. So each row represents the actual predictions and how well we predicted within a class. And you can see within our weekly predictions, we got 0 correct. 0 of our weekly predictions were actually weekly. And in fact, we only made 1 weekly prediction at all. And that was for the irregular class. However, within our majority classes, let's note the classification report. The support shows us how many examples there were in the test set for each class. And you can see that for weekly, we only had 193. So this is why we're getting such poor performance, because there's hardly any examples in there for the model to learn from compared to the others. The model is so much more focused on these ones because there's just so many more examples. And you can see within the monthly and irregular, we actually are misclassifying a few about equal. We're misclassifying some monthlies as irregulars, and we're misclassifying some irregulars as monthlies. Within our bullet class, we're doing fairly well. We have a few here and a few here, a few misclassified bullets. Sorry, a few monthlies and irregulars that we misclassified as a bullet, and then over here a few bullets that we misclassified as monthly and irregular. But more or less it's okay. However, our weekly column, you can see we just did terribly. We actually just got 0% accuracy on this column. So over here we have some precision, recall, and F1 score metrics. Precision is a measure of how well we did within our predictions in a given class. So that's looking at the columns. So precision for bullet is 94% because out of all of our bullet predictions, 94% of them are correct. Recall is saying out of all of the actual predictions, 96% of them are correct. So you can see that both of these are extremely high. In fact, they're high for every single one. The F1 score is just a combination of the precision and recall, sort of compounded into a single metric. But for weekly, we have zeros all across the board. So I would say the model is doing well, but it's not getting those weekly loans. Now maybe it's not so important. Maybe there weren't a lot of weekly loans, but if you wanted to build a model that can accurately recognize weekly loans, you'd want to employ some sort of maybe a resampling method to augment the data and get some extra weekly examples to boost the support of this, or you could bring down the number of the other ones to match this, or do something in between. We could also use class weights to try to weight the classes to get the model to care more about the weekly class. I'm not going to go into that, but that is something definitely to consider. But this will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.